Okay, so here we are. This is the first of these lecture worksheets. So today we are looking at, this is lecture 1.3. And this is rounding out our review in math. So I'm getting my calculator ready too, and you might want to have yours ready. So I looked at these steps. Now I want to point out that you can solve an equation many other ways, just like you can solve a metric prefix problem many ways. But the best way to do it, and this is the best way to do it, that I think is a way to show your work. So this shows your work, and you can also follow along clearly the work you showed to see what you might have done wrong. So this is what I ask is when you are given a problem, like a worksheet problem or a quiz question, and you're asked to show your work, you really need to do these steps. So it will get you to the right answer every single time, I promise, if you show your work in a stepwise manner. And if it doesn't get you to the right answer, then it will at least show you, you will easily find where you have gone wrong when you've actually written all this down in a stepwise process. Okay, so you do need these equations, which are given here, and you have lists of equations and conversion factors in the reference section of Canvas. Okay, but first let's take a look at this. Is problem number 1 that says calculate the volume in milliliter, this is meters. This is meters, lowercase m meters. We're going to talk about units next. The meters is the volume. And so the first thing that pops out is actually the unknown. They're asking you to calculate the volume. So I'm going to list that is the unknown. The unknown is volume. And instead of the word volume, what is more useful than the word volume is the symbol, the letter symbol that represents volume, which is uppercase V. Okay, why is that more useful? Because the letters, those symbols, is what you're looking for when you are searching for an equation, not the word, but the letter symbols. So even though volume, you have the units. Okay, so this is useful that you'll know that you're heading to the units of meters cubed. Well, you want to just, this V is the most important part. Now, continuing on, the other important information is you have a block of wood. Okay, so you might picture a block, but then it's the numbers are the important data. So these are the measured values. And so these are called the known information. So the known information is you have a width of 25 meters. So this is the width, and that width is not as useful as a word as you want the symbol, the letter symbol that represents width, which is a W. Okay, so you want to write that as a W and what it equals to, the number 25 with the units associated with it, M. So not just 25, but 25 meters. Because remember, a number value only is as important as its units. 25 meters is way different from $25, which is way different from $25 million. So you want the number with the units every single time. There are some rare cases where a number doesn't have units after it, but for the most part, if you're looking at a number, it better have something after it, a unit that represents what that number is. So the next is a length of 45 meters. So you're going to write the word length, which is not as useful as the symbol for length, that's L. And then the number value is 45 with meters. And then a height of 0.65 meters. So height, the word is not as useful as H, the symbol for height. And so that's 0.65 meters. So now that you have all of these, you can look for an equation with a V, a W, an L, and an H. So looking for an equation with all of those is this one. This is the equation. I'm going to copy that. It is the volume V of a cube is L times W times H. Okay, so this, what you're trying to solve for, the unknown, which is V, is already isolated. It is by itself on one side of the equal sign. So here's the equal sign, and V is alone. It's not multiplied by anything else. It's not in a denominator. It is by itself on one side of the equal sign. If this V, the unknown, is already isolated, then you don't have to do anything else to the equation. You can use the equation as it is. So I'm going to move this over here. So the V is length times width times height. when you don't need to rearrange the equation, you can plug in the values. Now the values are with the units. So the length is 45 meters times the width, that is 25 meters. So notice I'm putting in the number with the units. And then the height is 0.65 meters. So before going to the calculator, I'm going to deal with the units, which are meters times meters times meters. Those units are meters cubed. That's good because that's the units we were trying to get to. So once the units have checked out, notice I did not go to the calculator first. I calculated the meters, the units first. So sometimes you are canceling units. In this case, you're not canceling units. These units, though, were exactly what we're trying to get to, meters cubed. Okay. So once the units check out, you can go to the calculator. So putting all of this into the calculator is 45 times 25 times 0.65. All that in, you want to write the long number of the calculator. Now, in last week's worksheet examples, I had written the long number of the calculator, the entire complete number. And then I had written, we'll get to rounding it. Well, plenty of you guys didn't actually round the answers when it got to the worksheet answers. So when you are using a calculated value, you want to round to the correct sig figs or decimal places. And is it sig figs or is it decimal places? It's dependent on the type of calculation. For multiplication, you round to the sig figs. And this would be the sig figs of the least precise number value. So these number values are 45, and that has 2 sig figs, 25, that has 2 sig figs, and 0.65 has 2 sig figs because that leading 0 is not significant. So you need to look at the calculation. This is multiplication. That's going to be looking at sig figs, and then look at the original data to figure out which has the least number of sig figs. So rounding to 2 sig figs means that this is going to be 73 and not 73, but with a 0 because it was 731. So this is still going to be the 2 sig figs that are the 7 and 3, but you add a 0 as a placeholder and keep the units meters cubed. It's 730 and it's not 73. Okay, you don't want to put 73 because that is too far different from 731. The goal of this 0 is it is not a significant 0 because there's no decimal. And so it still has sig figs. This obeys the 2 sig figs, but it is close to the original number 731. Okay, so this would be the answer with 2 sig figs, 731 meters cubed. So let's take a look at number 2, which is a solid object has a mass of 35 grams. Now, the first thing that pops out here is some known information. It's not asking you the question of the mass, it's telling you the mass. So the known information is the mass. And mass is not as useful, the word mass is not as useful as the letter symbol for mass, which is M. Now, M is used a lot. That lowercase m is a prefix milli when it's a metric prefix. The lowercase m was also a unit meters when it's representing length. Well, here this lowercase m is the variable mass, okay? So this is 35 with the units grams. Now, how did I know it was mass? Because of the units of grams. So mass is measured in grams, pounds, ounces, but that will guide you to what the variable is, the lowercase m. So next is the density of 2.70 grams over centimeters cubed. So the density, which is an uppercase D symbol, you want to write 2.70 and then G over cm cubed. So then the unknown, which is this question asking you to solve for the volume. So again, the volume word is not as useful as volume, the symbol, the uppercase V. So you want to then go find an equation that has all 3 of these. You want M and D and V. So going back and looking at the equations, I see this equation that has a D, an M, and a V. Okay, so let's copy that equation. It has D equals M over V. Okay, so that's M over V. So this equation will help us get to the unknown, which is V. So I'm trying to solve for this unknown. Okay, so V is what I'm trying to solve for. And I circled the V in that equation. Now the problem is that this V is not isolated. It is not by itself on one side of the equal sign. So I first need to isolate that unknown. So isolate the unknown, which is that letter V. Okay, so what I'm going to do is in 2 steps. I'm going to multiply this across, or thinking of it this way, I can multiply V onto both sides of the equal sign. So this will be V times D equals M times V, and this is still over V. Okay, so all I did was I multiplied V on both sides. Another way you could think of this is cross multiplying. But what this does ultimately is it allows you to cancel out V. Okay, so that's first. We're still trying to isolate V. So then I want to divide by, or hold on, let me do this in the green that I had. I'm going to divide both sides by D. Why? Because I'm trying to get rid of the D that is next to this. So I want to divide both sides by D. Okay. And what this will give me is I'll be able to cancel that out. The D next to the V, which is the goal, is to isolate V, have it by itself on one side of the equal sign. And then what is left is that's crossed out. That's crossed out. What's left is this M over D. Okay, so what I did was I made sure that V is isolated. It's by itself on one side of the equal sign. Now I can use this equation, M over D. Okay, so you want to plug in the value for M, which is 35, and G, and then the value for D, which is 2.70 grams over centimeter cubed. Now this centimeters cubed is a denominator. It's the bottom of the fraction in another denominator. It's a fraction inside of a fraction. So what happens with fractions inside of fractions, such as this case, is the denominator will move. The denominator will move up and become times centimeters cubed. So when you have a fraction inside of a fraction, you want to make it a single fraction. And what this means is this is no longer there. It is multiplied times that. So it's grams times centimeters cubed. And then you can cancel the remaining G's. There's a G in the top and a G in the bottom. So what that means is that the units are centimeters cubed. Now check, does that make sense? Yes, that makes sense because centimeters cubed are the units for the volume of a solid. Just as these units above the volume of this block of wood, solid wood, is meters cubed. Well, this is the units for this volume of a solid object, the solid object, is centimeters cubed. So that's like meters cubed, except with the metric prefix centi in front of it. Okay, so once the units check out, they're units for volume, you can go to the calculator. So going to the calculator is going to be 35 divided by 2.70. And so writing this out, it's 12.9629626. That's the raw number from the calculator. Now you want to look at rounding this for either sig figs or decimal places. Because this is all this is all multiplication and division, you're going to look at sig figs. So this number has 35 has 2 sig figs, and this 2.70 has 3 sig figs. So I'm going to round this to 2 sig figs, the lower value, not the higher value, the lower value 2 sig figs. So rounding it to 2 sig figs means I'm going to keep the 1 and the 2. So the 1 and the 2, I look at the next digit, which is a 9, which means round up to 13. And the units are still going to be centimeters cubed. So that would be 2 sig figs. It's close to the original value, which is 12.9. So 13 makes sense. So not 1.3, not 130. And so 13 is rounding it to 2 sig figs.
I have a quick question.
So get used to these that are called molecular views. They are not what you can actually see because we cannot see atoms, we can't see molecules, we can't see compounds. They're too small. But these are how these atoms, molecules, and compounds are represented. And you will see these a lot in this class. So when you have individual single colors like this, these guys over here, these purple guys, I'm actually circling them in blue. These are individual atoms when you have individual circles. When they are only one color, you have just one type. So this is an individual element, and it is all one color. When you have one element, you have one color. When they're individual circles, it's called an atomic element. Those are called single atoms. Okay, so this could represent any of these types of elements on the periodic table. Majority of the elements on the periodic table, when they're out in nature, they are individual atoms, like Fe, that is iron, or Au, that is gold, or He, that's helium. So inside of a helium balloon, you cannot see the helium atoms, but what they are, they're individual little helium atoms. Or if you have a gold ring, that gold ring, you cannot see the individual atoms, but they are individual gold atoms. So the majority of atoms on the periodic table are individual atoms. They are called atomic elements. Now, some elements, just a few, a handful on the periodic table, are naturally present in nature, stuck together, called diatomic. So that's two atoms that are bonded together. But it's the same two atoms. So two atoms of hydrogen, or two atoms of nitrogen, or two atoms of oxygen, fluorine, chlorine, bromine, and iodine. These are still just elements because it's not two different elements. So it's just one element, but they're bonded together, which means it's not individual atoms anymore. That now you're talking about a molecule. So when you have two atoms bonded together, it's a molecule. When those atoms are exactly the same, it's called a molecular element. So there are 118 elements on the periodic table, and the majority of those 118 are individual atoms. They're called atomic elements. But these are the molecular elements. So this is how many of them? 4, 5, 6, 7. There's 7 molecular elements. So that means that you do have hydrogen as individual atoms, but those individual hydrogen atoms don't exist naturally when there are other individual hydrogen atoms around. That hydrogen, if there are little hydrogen atoms around, they will choose to bond together. And you will have hydrogen bonded to something else. So bonded to other atoms. An example being H2O, okay, which is a molecule, but now it's called a compound. When you have a compound, those are different elements that are bonded together. And so those you'll see different colors. So see, these were all purple, they're all one color. These are diatomic, these are hydrogen, this is H2. Those are two atoms of hydrogen, same color, stuck together, but because there's two, it's a molecule. Now, when you have a compound, this is different elements. So that means different colors is what you'll see, because each individual element is given its own color. So in these molecular views, these compounds appear as two different colors or shades. And this is this example of, here's a purple with a red, and they're smooshed together. That's a molecule. Okay, so when these are smooshed together, it's called a covalent bond. And I'm actually writing this down. When they're smooshed together, it's a covalent bond. Those are because electrons are shared. So those atoms no longer have their individual boundaries. They're no longer individual circles with circle shapes. They're smushed together and they lose some of their edges. Okay, and so that's called a molecule. They're smushed together with a covalent bond where the electrons are shared. We'll also talk about ionic bonds where the atoms are not smushed together, but these are all showing atoms smushed together. So these are molecules. Now, when you have the different colors, so this is one where you have white atoms bonded together with this black, this is a molecule. These are both called, they're molecules because the atoms are smushed together, and they're also compounds because you have different colors in there. So this is the same as true. This is a compound, and it's also molecules because those atoms are smushed together. Now, a mixture is sometimes people get confused with a mixture. A mixture is when you also have different colors of elements, but they are not bonded together. So they are not bonded together. And this is an example of a mixture of some purples and some reds. When they're not bonded together, they're just thrown together, and that's called a mixture. So it's a physical combination compared to a chemical combination. A chemical combination requires them being bonded together. So this is also on the right, a mixture, because you've got red, you've got blue, you've got this molecule. This is also a mixture. They're not all stuck together. They are different colors, they're different atoms, and they are all thrown together. So that's a physical combination called a mixture. Okay, so let's classify these down here. So you want to classify as an element, okay, a compound, or a mixture. Okay, so this first one on the left, this one. So I can see different colors. So when you have different colors and they're bonded together, that's going to be a compound. This is also can be classified as molecules because those atoms are smushed together. But different colors, that means compound. Okay, here, this next box over, these are two atoms smushed together. And this is all one color though. So that is an individual element. When it's all one color, that's one element, but there's two of these white atoms bonded together. So these are molecules. Okay, when you have atoms bonded together, smushed together, it's a molecule. So this is that diatomic element, an example of H2. Hydrogen is usually represented as white. This next box over, you've got these black atoms, then you've got this diatomic white atom. Well, when you have a physical combination where they're not all bonded together, this is a mixture. Okay, here's another, this box over. You have, this is a molecule with, this is a compound. You could also classify these as molecules because those atoms are smushed together. This is an element, that's that diatomic element. The diatomic element is officially called a molecular element. There are two white atoms, two hydrogen atoms bonded together, and that's a molecule. And so what you have though in this entire box, because they're not all of them bonded together, is that the entire thing is called a mixture. Okay, you have a mixture of a compound with an element. Okay, next row down, you've got this box, which is individual circles. These individual circles, these are individual atoms. When you have all one color though, it's an element. And those are showing individual atoms. That's the majority of elements on the periodic table. For black, it's usually going to be the carbon atoms, or C. Okay, and so this is called the atomic element. So this is an element in our element compound or mixture. And then this final box is, you've got a bunch of different things here. You've got these individual carbon atoms, those black atoms. You've got, this is a compound when it's a black smushed together with a white. This is another compound that's a black with two whites. You have these individual, this is an element. So when you got all of that thrown together and they're not all bonded together, then you're talking about a mixture. This is element symbols. And basically, when you are given a periodic table, it has information on there that you don't need to memorize. So the whole number value is called the atomic number. That atomic number is how many protons there are in the atom. It is a counted value. That's why it's a whole number value. If you've ever counted something, like count how many pens are sitting in front of in this container. How many pens do I have in there? That's going to be a whole number value. Anytime you do a count, an inventory, a head count, it's going to be a whole number value, not a fractional value. I don't have half pens. I don't have tenths of pens. I've got 1, 2, 3, 4, 5, 6, 7 pens in here. So it's a counted value, and that's why it is a whole number value. So that's called the atomic number. And what it is counting is the number of protons. Okay, and so we'll get to protons, but protons are a subatomic, smaller than the atom. So it's a subatomic particle with a positive charge. Okay, and we can't see those. You can't see those to count them. So that is given as the atomic number for every single element has an individual atomic number. It's like an address. Okay, then you have the element symbol. So the element symbol is representing one atom of that element, and it's usually going to be 1 or 2 letters. Okay, that element symbol is equal to the element name, and that's what we're practicing in the free rice. Is you need to know the element name because the periodic table you're given only has the symbols on them. Okay, so this is the symbol. It is 1 or 2 letters. Then you have the decimal value always given. That's the atomic mass. Now, why is it a decimal value, 52.00? So there's a decimal. It's because it's a calculated number value. It is a calculated mass that is an average. It's an average of all of the isotopes of that element in the universe. And it's the abundances, how much of all these isotopes. So you don't need to know that calculation, but you just need to know that it is a calculation. It is an averaged calculation, and that's why it is a decimal number value. It's called the atomic mass. Okay, you will see that roughly the atomic mass is about twice the value of the atomic number. So you can see there you've got 24 versus 52. That the atomic mass is usually about twice the amount of the atomic number. You don't need to memorize either of those numbers. You just need to know what they represent. Okay, so you don't need to memorize the symbols, but you do need to know the element name for the symbol. So these are the group numbers that are given here, 1A, 2A. And the reason why I gave you the group numbers is so you can basically, this is how they're organized, is that this is a family. Each is a family of elements in a single column. And as I mentioned in the video, when you have a vertical column, all of those elements are a family. They all have similar physical characteristics and similar chemical characteristics, not exactly the same, but close enough so that you could swap one out for the other, like the gallium spoon for the aluminum spoon, but not 100% close. Just like your human family, you can basically be, sometimes mistaken for a brother or an uncle or your parent, but not 100%. Okay, so you are close, similar characteristics, and same with the elements, similar physical and chemical characteristics. Okay, so going down here, so why are they organized like this? So they're listed by family, and all you need to know though is the element symbol is representing an element name. So going through these, this is sodium is the element symbol Na. So it's an uppercase. The first letter is always uppercase, and the second letter is never uppercase. The second letter is always lowercase. Okay, so this you could look up the remaining atomic number and family number. I'm going to get my periodic table here and find that the atomic number for sodium is 11. And this is in family number 1A. And you can look all of this on your periodic table. Strontium. So strontium is the element symbol Sr. So notice that sodium does not start with S. It is not So. It is Na because some of these elements that are older have names that go back to their Greek and Roman and Latin names. So this is coming from the old name. The original name for sodium was natrium. So the newer elements that were discovered, they tend to have the first letter is the element name. Okay, so strontium gets Sr, not St, but Sr. Okay, so strontium is in family 2A, and it is the element, the atomic number is 38. Okay, silicon, this got the symbol Si. So silicon is over here in family 4A, and it is the atomic number 14. Okay. Silver. Now, silver is one of those elements that's been around almost as long as humans could find it. And so it has the symbol Ag for its old name, agnethium. So silver is Ag, and it is the family number 1B. It's kind of in the middle of the periodic table, and it is atomic number 47. Sulfur is the symbol S. So when there's only one letter, it is just an uppercase letter. That symbol for sulfur, S, is in family, you'll find it in family 6A, and it is the atomic number 16. Copper is another one of the precious metals found on Earth, and has the old name. It is not Co for the element symbol. Cobalt actually is Co. Copper is Cu, coming from its old Latin name, cuprium. Copper can be found in family 1B, and this is the atomic number 29. Now, cobalt is Co. So cobalt got the Co, not copper. And cobalt is in family 8B, also kind of in the middle of the periodic table, and it has the atomic number 27. Chlorine. This is the same chlorine that's used in swimming pools for disinfection. Chlorine is not CH, but it is Cl. Okay, so it is Cl for the element symbol. It has the atomic number of 17, and it is in family 7A. And then finally, carbon is the symbol C, and it's just the one letter C, uppercase. And then it's the atomic number 6, and it's in family number 4A. So you'll notice I can use a periodic table for this information. So use the periodic table, but that the periodic table is not going to have the element names on them. You are now, hopefully, have your eyes opened to this periodic table, and you don't see just a bunch of boxes with a bunch of letters, that these letters, these numbers all represent things. And also that this is not some haphazard arrangement of boxes. It is a purposeful arrangement of boxes so that it's organized by families in vertical columns. It's organized based on this stair-step line. This is this stair-step line that I'm highlighting in blue. To the left of the stair-step line, you have metals. To the right of the stair-step line, you have non-metals. And right on the stair-step line, those are called the metalloids. Like this silicon is a metalloid, or this germanium is a metalloid, Ge. Okay, and so you have an organization describing their physical characteristics and the individual families. So this is a family. Those elements have similar chemical and physical characteristics. And then also there's the organization in which you can see that this is counting across and down. So 1, 2, 3, 4, 5, 6. That's organized by an increasing atomic number. So the overall organization is by increasing atomic number. This is by counting over and down the whole number values. Okay, but it's organized on several levels. And so that's why, I mean, how can you not appreciate this several level organization, right? And so when you understand what you're looking at, then you can find a lot of information from the periodic table. So for instance, this is a box. These boxes are just showing the organization of the periodic table. And what can you know from just how these boxes are arranged? Okay, and so I don't think I got to this part yet. I have not yet gotten to this part. Okay, so the part we have not named the elements as families. So this I'll get to. The alkali metals are in family 1A. They're called alkali metals. Okay, so everything in family 1A is called an alkali metal, and everything in family 2A is called an alkaline earth metal. Okay, So if I label this on this periodic table, this is family 1A, this column, and this is family 2A, that column. And you can confirm this going back up to this periodic table. This is family 1A number at the top, and that's family 2A number at the top. And seeing how these numbers of the family number, that's the family number, they increase going across to the right, 1A, 2A, but then jumping over, here's 3A, 4A, 5A, 6A, 7A, and 8A. Okay, so those two families, I'll rewrite them here. This is called the alkali metals. And this family number 2A is called the alkaline earth metals. They're very similar, and they are given the names, which means that you could say that any individual element is an alkali metal. So hydrogen is an alkali metal. Lithium, Li, is an alkali metal. Na, sodium, is an alkali metal. It's the general name of the family. It's kind of like the last name of your family. Everyone has the same last name. So this is the family name of 2A, the alkaline earth metals. And then family 7A also has a family name. They're called the halogens. And family 8A has a family name of the noble gases. Okay, and so these are the descriptions of here. When looking at family 1A, the alkali metals are this letter I and this letter C are called alkali metals because they're in that vertical column that is family 1A called the alkali metals. Family 2A, this is this letter F, that's called the alkaline earth metals. So you would know this box is an alkaline earth metal. Okay, going back up here, you have this stair-step line. Let me highlight this in red. No, don't do that. Okay, do this. Where you have the stair-step line. Okay, you have to the left of the stair-step line are the metals, to the right of the non-metals, but actually on the line, those were called metalloids. Those are also called semi-metals or semiconductors. And I mentioned silicon. Silicon here in this box is a semiconductor. It is a semiconductor used in computer chips because it conducts metal, or it conducts heat and electricity a little bit. It can conduct it in a controlled manner. And so that's why silicon is used in a computer chip, is that you can turn on and off the flow of electricity, and that's your zeros and ones that allow for computer processing. And so another use of this periodic table is to replace silicon, because if you've ever had a computer chip die on you, you know that silicon is not perfect because it conducts heat with the electricity. So it's conducting the electricity in a controlled manner, but also heat goes through, and that's why your silicon chip ends up burning out. That germanium is being researched to replace silicon. Now, why did they choose germanium as opposed to anything else on the periodic table? Because germanium is directly below silicon. It's in the same family, so it will have similar chemical and physical characteristics. It should act the same as silicon, but it might be slightly better and not conduct heat as well. So germanium the idea is to have some replacement for silicon because chips do burn out. Okay, so this is a semiconductor, would be something on that stair-step line, which is this one B. That would be that silicon example. Okay, when you are talking about these other two families, I'm going to rewrite this here. The family 7A is called halogens. Now that family are very reactive gases. We'll talk about why those are very reactive gases, but every element in this family 7A, that's fluorine, chlorine, bromine, iodine, or F, Cl, Br, and I, those are all gases and they're very reactive. And this is in comparison to family 8A, which is right next to it. The column next to it are called the noble gases. These are non-reactive gases. Why they're called noble is because somebody who's noble rises above things and they're not reactive. So these gases, this column, this vertical column 8A, These are not reactive. So the helium, the neon, the argon, the krypton. So it's why you can give a kid a helium balloon and know that there's not going to be any explosion of that balloon, because inside of it, that helium is not reactive. The only thing that balloon is going to do is pop. It's not going to blow up. It's not going to react. Okay. So this is every element in family 8A. These are noble gases. They're not reactive. So helium, neon, argon, krypton, not reactive. And so that's Kr krypton, different from kryptonite, which is some invented element, does not exist. But in the Superman Marvel world, it is kryptonite. It is not any element on the periodic table. So your non-reactive gas, this would be something in family 8A. And finding something in family 8A would be marking this on this box, 8A. And that would be this box A. Okay. And so when you have a reactive non-metal, so a non-metal like a gas, I'll put this non-metal here. So this is to the right of the stair-step line of your non-metals, and these are those gases. And this is in family 7A, and that would be family 7A, your reactive non-metals, that gas, and that is going to be H, that box H. Okay. Not all the letters are accounted for. That's okay. But when you have a bunch of boxes like this that represent the periodic table, you know a lot more than you know. They're not just a bunch of random boxes. Okay. Let me get to